All right, let's go over our last subunit of the electron configurations unit, quantum numbers. This one might be a little difficult, but it's okay. We can practice in class as long as there are forum questions. Otherwise, I assume you got it, and we will move on, like I've said, every unit or every lesson. So today, there are 4 quantum numbers. We're going to be able to identify them and what their names are and what their symbols are, what they represent. We're going to be able to write the quantum numbers to describe the electron's position in an atom, and we're going to be able to identify any electron based on quantum numbers. So you know how we have electron configuration, and then we we can either write the electron configuration for an atom, or we can identify an atom based on its electron configuration. So basically, we're going to go backwards and forwards on quantum numbers as well. Okay, so quantum numbers, so it's kind of like electron configuration, but nothing like it. Again, these numbers are used to explain where an electron is in an atom, and kind of what it's doing as well, okay? So there are 4 quantum numbers. There's the N, L, M sub L, and then M sub S. These names look a little intimidating, but basically actually I think I have it in the next slide, but N is just the energy level, L is just the orbital, like the S, P, D, or F, so like L would represent this sphere, okay, the shape of it. M sub L would represent its orientation, so whether the orientation of the D, so this would be a D since it's double clover, so if it's on the, for you guys, I think, no, this would be X plane, Y plane, and then like a Z, I don't know. It's kind of confusing because the camera's upside down, but it's orientation of how these things are. So if they're like facing towards you, or if they're going on an X, Y, or Z plane, some of them have more planes, some of them only have one, like this guy only has one plane. This is how he's oriented. And then there's the spin quantum number. And we'll talk about why we say there's a spin quantum number, and that's indicating that the electron is solid, and this whole model is based off of an electron being a wave type thing, when actually the spin makes it sound like it's a particle. So the spin we'll talk about, it's basically more, it's a property of a wave, but it's basically kind of like opposite. You have to have spin to have a wave, but it's not really like, don't think of it as like this is spinning, okay? Don't think of it as a rotation. Okay, so the principal quantum number, like I told you, it's just the distance the electrons have from the nucleus. So the principal quantum number, let's say we have this nucleus, okay? I told you guys, the Bohr Rutherford doesn't go away. So we have a nucleus, and then we have this energy level, okay? So this is, that's what the first quantum number is the energy level. N equals 1. It's the first energy level, okay? And then we have if we were to draw a second energy level, okay? The second one, N, would equal 2, okay? There is no 1.5, there is no 2.5. Electrons are either here or there. They're not in between. And obviously, the larger the value, the further from the nucleus. The next one would be 3, 4, 5, and they're getting further away from the nucleus. Angular momentum quantum number, all that is just the shape, okay? So, for example, if you have a 0 angular momentum quantum number, okay, it's these words you have to get used to. But if you have a 0, you have this shape, okay? That's all it's saying, is it's the shape, okay? If you have a 1, quantum number, angular momentum quantum number, okay, the L, okay. If you have a 1, the shape is like this. Ignore all the spikes. Okay, if you have a 1, the shape is this, okay? If you have a 2, you get the point, right? If you have a 2, your shape is the clover. I'm not going to do this. I'm going to stab myself. But you get it, right? If you have a 2, it's shaped like the d orbital. If you have a 3, it's shaped like the f. So guys, keep in mind, okay, for those of you going to college and going to IB, there's this thing called hybridization, okay, that I am not teaching in 10th grade, okay? And what happens is when you add more electrons into these orbitals, like let's say into the p orbital or into a d orbital, there's weird things that happen to the shape. So they're not all like, this is always the shape of this sub level. So keep in mind there's this thing called hybridization. We don't learn that in 10th grade, but you will actually learn it in IB. But it's no big deal. It's just a different shape, and they're actually pretty cool shapes. Okay, so an example, we already have an example. So what does L equal if n equals 1, n equals 2, or what if n equals 3? So the question says, what is L if n equals 1? Let's just look at that first. Oh my gosh. If n equals 1, okay, so n equals 1, here's the sub-level, okay, or here's the n equals 1. It's that first energy level. If n equals 1, L can only have the S shape. And if you'll look back, the S shape is 0, okay? So, which equals 0. So if n equals 1, then L must equal 0, okay? How you know that is you would take the number of n, you subtract 1, and that's your L. So easy, okay? Quick maths, okay? So if n equals 2, okay, let's go. If n equals 2, then L equals basically 2 minus 1. So L equals 1, okay? But keep in mind, okay, energy level, you could have an S or a P, okay? So n equals 1 and 0. Sorry, and 0. All right? So if, let's do a different color. If n equals 3, L will for sure equal 3 minus 1. Wow, that's bad. So L will equal 2. Okay? So in the third sublevel, you have an S orbital. So 2, remember, is the D orbital, okay? So D. In order to have D, you must have filled a P, and you must have filled an S. So you will have a 2, a 1, and a 0, okay? You'll have an SP and a D orbital, sublevel. Okay, so that's easy. L will equal whatever n minus 1 is. All right, now magnetic quantum number. So remember the N, this number represents the energy levels. This number represents what that shape is in there. Okay, so whether it's an S orbital, a sublevel, P or D or F. Now M sub L. So M sub L, that is orientation. So these things, even though you have this P, you have 3 of them, okay? They're not 3 stacked on top of each other. You have one here, and then you have another one kind of going across on it, and then you have another one just kind of going outwards, like into the screen, okay? So that's just the orientation. So if you have an S, okay, then there's only one orientation. If you have a P, there's 3 orientations. So, and then D, there's 5. F, there's 7. It's just like the remember the orbital notation with the circles? That's what it's like. Okay, so it's just orientation. So it's basically M is negative L all the way to positive L. So if L is 0, okay, if L is 0, then the M sub L has to equal 0 as well, because negative 0 to positive 0 is still 0, okay? If M sub L, if L equals 1, okay, then you would have, so if L equaled 1, this is if L equaled, whoops, sorry, fisticky no. If L equals 0, then M equals 0. If L equals 1, then M sub L would equal minus 1, 0, plus 1, okay? If L equaled 2, okay, then the M sub L would equal minus 2, minus 1, 0, plus 1, plus 2. Okay, so it would have 5 different orientations. This is the d orbital, that's why there's 5. This is the p orbital, that's why there's 3. There's 3 circles in that orbital notation. This is 5 circles, remember, guys? And if you don't remember, you really need to watch the previous videos. And we already did this slide, sorry. Okay, so electron spin quantum number, so m sub s. We'll flip it, spin it, ha ha ha. Okay, so m sub s, you're either going to have a plus 1/2 or minus 1/2. Okay. So electron spin in 2 directions only, up or down. Always valued at plus 1/2 or minus 1/2. The plus 1/2 corresponds to the up arrow, and this one corresponds to the down arrow. Please remember, to be a wave, there is this spin, and basically don't think of the electron as this tiny ball kind of spinning around, okay? That's representing a tiny ball spinning around. I suck at drawing. Anyways, it's not this tiny ball rotating like this, okay? Remember the spin, in order to have a wave, just know that this would be the plus 1/2. This would be the minus 1/2. It's not actually rotating, okay? It's just the opposite phase of the wave, okay? Oh yeah, moving on. So let's do some example problems. This might help you, okay? So list the values for N, L, and M sub L for the 4D sub level. Okay, so it wants N, it wants L, and it wants M sub L. Fisticky. For the 4D sublevel, okay? So 4D, it gives us our N right there, literally. So that's it, 4, okay? 4D. And then L, so if L equals 4, if N equals 4, L will equal 3, okay? Also, 4 minus 1 is 3. Also, you could look at this, okay? Remember on the slide, S equals 0, P equals 1, D equals, S equals 0, P1, D2, whoops. We're going to say it's 2. D equals 2, F equals 3, okay? So D will equal 2, okay? But in the 4th energy level, you could have had up to an F. The F sublevel starts at 4. That's why I wrote 3. I'm so sorry. But we're talking about D, so it's 2. And then the M sub L. So basically, M sub L, remember, it goes from negative L to positive L. So M sub L would be negative 2, negative 1, 0, 1, 2. Okay? That's it. So N equals 4. L equals 2. Okay, those are just the choices. You could have had, let's write it in black because it's not true. 0 in the 4th sublevel, you have an S orbital, S subunit, you have a P sublevel, I keep saying subunit, S sublevel, P sublevel, D sublevel, and there's also F sublevel in the 4th energy level. So these right here, these guys start at 4, okay? I'm sorry, guys, I have a cough. Okay, so we are correct. I can't believe it. All right, next question or example. Write the 4 quantum numbers for each electron in a 2s orbital. Okay, so now it's asking us to write the 4 quantum numbers. So all 4, not just the 3, for a 2s orbital. So we need to write an N, an L, an M sub L, and an M sub s for each electron in a 2s orbital. Now, we have to know how many electrons are in a 2s orbital, okay? So we have one, 2 electrons in the s orbital, okay? So 2. So we have to do this for 2. So the first electron will have these quantum numbers. The second electron, so electron number 1, electron number 2, will have these quantum numbers. Okay, so both of these, we'll change colors, both of these energy levels are in the second energy level. That tells us, that's super easy, okay? You should always get at least part of these correct because they're really easy. This is S, remember S is 0, P is 1, D is 2, F is 3. So this is 0, okay, for both of them. M sub L, so both of them, M sub L, remember, is negative L to positive L. Since it's 0, it's going to both be 0 as well. And then the spin. So remember, each electron has its own spin. It's either an up arrow or a down arrow, okay? So one's going to be the up arrow, or with a positive spin, and the second one will be with a negative spin, okay? So that's the 4 quantum numbers for the 2 electrons in 2s. So we're basically talking about these guys right here, okay? This lithium, this is lithium's quantum numbers. This beryllium, these are beryllium's quantum numbers. Oops, you can't see. This is lithium's quantum numbers, beryllium's quantum numbers. Okay, let's see if we're right. Yep, we're right. Okay, oh, I didn't show it, but you can draw it as well. So I like to, here and here. Keep in mind, each one of these lines represents a circle, which actually we need just one since it's an S. So each line would represent like a circle for orbital notation. So we are in 2s, okay? So this one would be spinning up and this one would be spinning down. Otherwise, it's the same. Okay, and there you are. Sorry, this might also be helpful. I'm sure you can see on the PowerPoint, but this is the quantum numbers for that one. These are the quantum numbers for that electron. Okay, so all 4 quantum numbers for all electrons in the 3p orbital. So basically we're writing all 4 quantum numbers in the 3p orbital. Let's get started. So first we need to look at the 3p orbital. How many electrons are we talking about? It doesn't tell us, so we have to figure it out ourselves. Here's 2p, here's 3p. So we're basically looking at, if I can find my, I'll do this one. We're basically looking at all electrons here. Okay, we're going to assign a quantum number for aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Okay, that's what we're doing. Okay, so we have the 3p orbital. All right, so there are 6 electrons in that 3p orbital. So we have 1, so electron number 1, electron number 2, electron number 3, electron number 4, electron number 5, and electron number 6. Okay, so we have all 6 electrons, and we're going to tell the quantum numbers. So each one will have a quantum number. We have N, L, M sub L, M sub S, okay, for each one. L, M sub L, M sub S, N, L, sorry. It's best that you do this along with me too, so you kind of get used to writing these weird things. It's not This isn't something you use every day, so it's new. So I would write it so you know how to set it up. This is how I set it up. Some people may set it up differently. So anyways, 3p orbital. So 3p, go ahead and write your orbital notation. So I'm going to go ahead and write my 3 lines, which would be like your 3 circles for the orbital notation. Okay, so all 4 in the energy 3p. So we have 3p, so all of the n's, that's easy, right? All of the n's will equal 3. So 3, 3, 3, 3, 3, and 3. P, they're all in the p sublevel. So remember, just like a recap, S equals 0, P equals 1, D equals 2, F equals 3. Okay, you just got to kind of know these numbers, what they represent. We put a number on them, that's all they are. So we're all talking about P, so that's 1. So all of the L's are 1, okay? And all of the M sub L's means that it's -1 to +1, okay? -1 to +1, -1 to +1, okay? It's not LOL. Okay, and then go ahead and write it here. That's what this number represents, 0 to +1, okay? There are 3 orientations. There's an X, there's a Y, and then there's one coming at you. Okay, so basically, these spins. So we have 3 possible orientations, okay? And in each orientation, you can fit only 2 electrons in it, okay? So we're actually not going to find this electron in all 3, okay? We're going to circle which one we find it in, okay? And I'll show you what that means. And then the spin. So I like to find these 2 together at the end. These 2 they're always really easy to find. These 2, you kind of have to fill this out to find these, okay? So first one, let's go ahead and use black. So first one right here, we're going to fill in our first arrow, okay? Just like orbital notation. So the first electron, which is here, okay? The first electron, which is here, is in the -1 orientation, okay? So this is actually the answer, not these, okay? -1 orientation, and it is spinning up, so it is a +1/2. Okay, next one. Remember, we can't fill this one in until we filled 1 in each, 1 electron in each. We cannot do our down arrow yet. So the second electron, it's right here, okay? So it's in the 0 orientation. So this is the correct answer, and these 2 we ignore, okay? And it's spinning up, +1/2, okay? Next one has to go, the third one, here, okay? It's spinning up in the +1 orientation. So these 2 are out, and this one is in, okay? You'll see a trend, and you might, once you do these a lot, you might just know, okay, -1, 0, +1, -1, 0, +1. But just in case, for now, I'm just trying to show you the raw process. And then looking at the 4th electron, we filled 1 electron in each orientation. So now we can go back down and fill our down arrow, okay? So that means it's -1/2. It is spinning down, and it's in the -1 orientation, okay? Then we move on, we put this one here. It's in the 0, okay? 0, and it's spinning down. You'll know to do +++, minus, but until you're comfortable with it, I'm just showing you. The last one, spinning down in the +1 orientation. Spinning down in the +1 orientation. Okay, so let's see if we're right. Okay, so yeah, we're good. We're good. We filled it out. in order from first to sixth. The other one, it didn't fill out in order, and that's totally fine. It just went from the orientations. I filled it out in order of putting in the arrows. It's okay, because you just need the list of the correct ones, and we have them all. So we're good. That's it. That's quantum numbers.